role with the company. So I will start off with myself. I'm a mathematician by training, and I have 10 years experience in banking industry across 3 Canadian banks as a model developer for 5 years and a model validator for another 5 years. So let's start maybe with alphabetically. I don't know, doesn't matter. Armando, maybe from BMO Capital Markets. Would you like to say a few words about your background and your career?
Yeah, absolutely. Thank you for inviting us, Letitia. It's an honor to be here and sharing the panel with so many great industry leaders. My name is Armando. I work at BMO Capital Markets. My focus is front office applications. Some of them do have AI as a fundamental piece, but many others are applications to solve business problems. And I think that is one of the things that I've been focusing on my career, using data in interesting ways. I started as a high energy physicist that was analyzing proton-proton collisions at the CERN, at the Large Hadron Collider. From that, I realized that there was a huge potential of using the same type of techniques and statistical analysis outside the research and academic world. And I ended up at a tech company, a mobile marketplace with, I think today, close to 500 million users. There are a lot of interesting challenges in that aspect, in that particular world. Things like fraud detection, recommender systems become really challenging when you have that large amount of data. And then I was very active in the Toronto community. This, of course, all pre-COVID. So I had a meetup at that point. That was when deep learning and machine learning was starting to take off. This about, I don't know, 6 years or so. And I was the organizer of one of the meetups in Toronto, the deep learning meetup. And through that, I met someone from BMO, and we started having conversations about the intersection of finance and machine learning. A lot of people in physics do end up going to finance. I wanted to stay away from it, but now I'm here. And so the reason why I was attracted was because there was an interesting opportunity of putting those two intersections together, creating a very unique type of like greenfield opportunity. There was a lot of there was nothing done really, or very minimal. So that to me, it is a great place to start, just because you have the full spectrum of opportunities to take advantage. So yeah, my team focuses on front office applications for trading, and mainly we focus on revenue generation. We started as part of one of the business and on the equities world, and we identified that we could do the same thing and scale the same type of operations across the whole firm. And effectively, one of the things that we do is remove the gut feeling out of the decision-making process. My group started, as I said, on the AI part, but now I am responsible also for the full quantitative engineering team, which follows the same principles, right? We use ultimately write software to solve business problems. Yeah, that's me. And again, happy to be here.
Thank you. It's a pleasure to have you here. By all means, feel free to jump in. Greg, maybe, or I don't have to.
Me? Hello.
Hi.
Hi, I'm Greg Kirczenow. I work for RBC, and I do model risk management at RBC, specifically focused on machine learning models. So my team, I lead a small team of data scientists focused specifically on basically testing machine learning models that are developed at the bank. We have enterprise scope, so really any application of machine learning in the organization, we look at that. So it's, to me, very fascinating that just the wide array of uses of machine learning in finance, especially in areas that you might not think would be useful in finance, like NLP, for example. There's quite a bit in the bank. And we've spent the past couple years trying to understand exactly how should we apply model risk regulations like E23 to machine learning, where things are a little bit different. You've got fairness, explainability, these sorts of things that that people think about. And so, in a broad sense, my view is that the model risk regulations are very broad and apply very well to machine learning. So there's no need to change them, but the difficulty is figuring out how do you apply them in a space that's a bit different. So my team has been working at that for a while now, and I think at this point we have pretty good answers for how we validate those models across really the entire spectrum of use cases for different businesses, from credit to capital markets to commercial banking, and also quite a wide variety of algorithms. Of course, the supervised learning, but also reinforcement learning. There's a fair bit of unsupervised learning in the bank these days too.
Right. Thank you. Excellent, Greg. Andrew Brown. Yes, from CIBC.
Thanks for the invitation to come speak.
Pleasure.
Well, I'm currently with CIBC Capital Markets. I've been with the bank for many years. My background was in computer science and machine learning, and I guess I joined the institution at a time when those things were not so well known or understood, and we started out in a group that was trying to apply them to some common business problems like customer behavior modeling, prepayment risk in mortgages, or credit risk in loans. And I sort of migrated through some different groups in Treasury, applying sort of those principles of data analysis and modeling to customer behavior and how we manage interest rate risk within the bank. And then I guess most recently I was with the Enterprise Advanced Analytics team for a number of years, and that group is like a service center for the organization, working with different groups, different businesses on trying to tackle their problems that could be solved with data and analytics. And across CIBC there are multiple groups. The enterprise team, and then within different lines of business they have their own analytics groups, and also there are people applying machine learning concepts and modeling approaches across the organization. I'd say like some of the use cases we've tackled are focused on personalization, particularly in the retail and wealth management spaces, like how to do appropriate messaging and marketing, and understanding client turnover, applying analytics processes to fraud, improving how that can be done using machine learning techniques, and exploiting access to wider sets of data to try to stem fraud problems. And then as Greg mentioned, NLP shows up in a lot of places, particularly with contact center or client experience, being able to just analyze large volumes of client interactions to see trends, and assist the contact center or the digital teams, or even our virtual agent teams, in understanding sort of where client journeys are not are sort of breaking down, and how to augment their processes to handle that. And lastly, we've had some success applying machine learning to operations, integrating sort of in-house machine learning models with RPA processes, so that you have bots that are automating these kind of manual processes, and then the more complex decision making can be passed off to a machine learning algorithm. And I'd say also the analytics team at CIBC is leading in terms of handling some of the new issues that arise with respect to deployment of machine learning, like around explainability and fairness and operationalization.
Excellent. Thank you, Andrew. Let's go to Shelly.
Yep. Thank you, Letitia, for having me. Shelly Liposky, I lead our business risk and solutions team at BMO Capital Markets. The mandate that we have is this is in the line of business to predict and prevent operational losses and ensure we execute our business in compliance with applicable regulations. So the areas of risk that we focus on are supervising the trading floor, anti-money laundering, operational risk and resilience, algorithm and automation risk, and ESG risk. And I think the most relevant part of this for this panel is our operational risk area. So my background again was doing M&A, and then I moved into COO roles, and always had this intersection with operational risk. And it was typically very backward looking. Somebody would fat finger a trade or make a mistake in operations, or there was a fraud, and somebody else would write it on a piece of paper and eventually type it into a system and then put it on a PowerPoint deck, and then it was discussed in a committee meeting. And that was very backward looking. We were always reacting after an operational loss happened. And so when I became responsible for business risk in the area of operational risk, I wanted to use machine learning and AI to be able to predict when losses were likely so we could prevent them. And so one tool that we've created is called OLI, O-L-I, which stands for Operational Loss Intelligence. And OLI ingests internal data and external data and produces a signal that allows us to understand when a trading desk or an operations group or a set of clients has a higher risk of a loss, or in the case of clients, higher risk of fraud. And then we use our response protocol to change behavior to prevent that loss or that fraud from happening. And so what we're using AI and machine learning for here is an application where we're bringing internal loss or client or behavioral data together with external terabytes of market and economic data that we put through our proprietary machine learning models. And then we get a signal, and depending on the threshold, it's going to drive action or it's not going to drive action. But the goal is to change behavior. And I think that the ability not only to create models that tell us something, that's one thing, and it's very important to be able to do that. But if the business problem we're solving for is to prevent losses, and most of our processes continue to be manual or somewhat manual, then we have to actually change the humans that are executing those processes. And I think that's an example of where we bring human plus machine together to enhance our business and to drive profitability.
Excellent. Thank you, Shelly.
Yep.
Let's go to Maxime. Hi.
Yeah, thank you for having me. I'm Maxime Bergeron. I work for RiskFuel, where I head the research and development as well as production. My background, like Letitia, is actually pure mathematics originally a long time ago. And mainly my focus was understanding the shape of points in very high dimensional spaces. So a few years ago, I was a faculty member at the University of Chicago when I met Ryan Ferguson, the founder of RiskFuel. And he started talking to me a bit about the issue of understanding the input space of very high dimensional pricers if you want to create training data to then replicate them using deep neural nets. So he hooked me pretty good. So I resigned from the University of Chicago and joined RiskFuel. And it's been quite the ride since then. For me, the entry here that's interesting is that this is a very kind of bare knuckles approach to machine learning. Like, we're not doing any fancy NLP stuff or predicting stuff. We're just using the original application, which is, can we replicate an arbitrarily complicated function? The cool thing is, you know that it's true, you can do it, but only in theory. So the hard part is figuring out those things in practice. So basically what my team works on at RiskFuel is, we start with a typical Monte Carlo pricer. Those are really nice. You can price anything you want and you can get it as accurately as you want. The catch is you have to slow it way down. So typically what people do is they dial down the accuracy until the noise just becomes too much to bear, and that's what they run in production. But obviously that's a bottleneck. And so you end up with the model you can run and not the model that you want. So forget about your local stochastic volatility or the likes. So the cool thing is that you can actually bifurcate time and accuracy using deep neural networks, right? You can build the model that you want to the accuracy that you want, and it can be as slow as you want, because then you can build a neural network that will replicate it arbitrarily well and obviously run 1,000,000 times faster. And that's not an exaggeration. Clearly, this is not as easy as it sounds. Like, we have a team of about 25 people that have been tackling this problem full time for a few years now, but it's not just theory anymore, it's in practice. Many people at this panel will know that we've done work in production with Scotiabank. We work with BMO, we work with HSBC, Bermudan swaption, auto-callables, vol swaps, whatever you want. That's the kind of thing that we've been tackling.
Excellent. Yeah, thank you. We will dive in later in more specific use cases. For now, Ignacio, would you like to go next?
Yes, thank you, Letitia. Thanks for having me here. And similar to a lot of people in the panel, my background is in physics instead of, well, mathematics or physics, very kind of cousins from each other in many ways. And the type of, I've been working on this field for around 7 years now, in the field of something very similar, highly connected to what Maxime just explained, which is, I work right now in Scotiabank in the Counterparty risk analytics team. And one of the challenges that we have is exactly what Maxime just explained, is that if we do the computation that we would like to do, not that we can, then the computational time explodes to the point that we actually do what we can as opposed to what we want to do. And I've been working in a very similar fashion to Maxime in terms of how we can use different numerical methods and machine learning methods to obtain, at the end of the day, the same calculation, but in a much efficiently, much faster, basically, or much cheaply from the computational point of view. And that, of course, that was the starting point, because once you are able to do a calculation that before was taking you 3 hours, now you can do it in 3 minutes. It's not only just that you make it faster or cheaper, is that now you can do many things that before were actually unthinkable. So that is the field in which I specialize. I recently, early this year, I published a book in Wiley Finance, or called actually Machine Learning for Risk Calculations, in which we explore, with my co-author, we explore a number of techniques that can be used in the context of counterparty risk, in the context of XVA pricing, the context of market risk, volatility, surface calibration, a number of things. And we discuss, in fact, different techniques, not only deep neural networks, which of course is very useful in many ways, but also we explore other techniques like Chebyshev tensors, that is in fact becoming increasingly popular as well. How and when to use one and when to use the other one. And that is basically the area in which I specialize, how to accelerate risk calculations.
Thank you so much. And let's go to Andrew from Thinking.AI.
Hi, I'm Andrew Weeb. I'm the CTO and Chief Scientist at Risk Thinking. I'm standing in for Ron Dembo, our CEO, who is stuck overseas. So he is in a different time zone. My background is I'm a climate scientist / meteorologist. I built weather forecasting systems and decision support tools for industry and governments for about 20 years all over the world. Really bringing in a lot of satellite data, numerical data, observational data, and turning it into something useful that you can make decisions out of. From the experience of doing that and building all those technologies and harnessing the hardware, the software, and the data, we sort of pulled all that together into what we call RiskThinking.AI now, where we're looking at climate risk and transition risks and applying them to the financial industry. So looking at how all those different projections of the future from the IPCC and the CMIP6 models, from the physical climate through to the integrated assessment models from economic perspective and econometrics, how do those interrelate and how do they operate and how do they project out into the future? So what is the risk profile of a company in 2050 compared to today? To achieve that, we use obviously a lot of data, also a lot of machine learning, and a lot of new techniques and integrating techniques like graph theory and with semantic ontologies, with NLP, with knowledge graphs, with then running neural nets on those to then create these relationships of how do these risks impact particular places and people and things. Yeah, so we use a lot of different techniques and a lot of data, and it's all future looking as well as your baseline. So it covers all the aspects of AI and machine learning.
Great, excellent. I'm happy to see that we can use AI to forecast various climate scenarios in the future. So we'll discuss more later.
Yeah.
Different applications of AI, not only in banking.
Absolutely, and so, just a side note there, with how I got into machine learning was from the climate side, where we're doing a lot of bias correction and data assimilation and parameterizations, and you end up using those techniques to do that. So I started doing it so long ago with Fortran 77, and we called it advanced time series analysis. And then I had a student that told me that's machine learning, and I was like, oh, is that what it's called?
Excellent, thank you. I hand it over to Rustam. Happy to have you here. Hi, Rustam. Yeah, can you hear me? Can you hear me?
All right,
I hand it over to you. Happy to have you here.
Thanks, Letitia. Thanks for inviting me. It's a pleasure to be here. Lots of interesting people, different backgrounds, and very interesting applications and use of AI machine learning. So my name is Rustam. I'm currently at TD. I lead the AI and machine learning model validation team. I've been with the bank for about 5 years, I'd say, almost 5 years. And all of those 5 years I was, and still am, with the model risk management team in the model validation function. So I started with validating traditional financial, I would say, macroeconomic models, since my background is in economics, econometrics, and finance, more like statistics. So I did, validation of different macroeconomic models, finance models, yield curves, all of that, and then slowly transitioned into the machine learning world of models once they started being in scope, and we started seeing more and more of them. And now I solely focus on those models. It's been a very interesting journey for sure. I did have an interest in machine learning models and algorithms back in my student days, doing my grad studies. Took courses, read books and articles. Back when I was a student, there were no specialized programs called, Masters in Machine Learning or Masters in AI. It was just, you would read whatever's out there, research papers, online courses, however few of them there were, books. So personal interest of mine really helped me when I started working at TD. I was looking for work as data scientist, but also work within the financial industry, given my background. It just so happened that I ended up in the world of finance. But then I was lucky enough that my interest in machine learning helped to transition into that world. We started seeing machine learning models, I think it was 2019, something when they became in scope. We have initially seen models for credit risk, for insurance, businesses, and then it's sort of the inventory kind of exploded in 2020, 2021, I think, with all sorts of different use cases. And that's what I love about the model validation, model risk management, because you get to see, various business uses of machine learning models, different use cases, different algorithms being utilized for different use cases. You get to see the creativity that's out there that the model developers have in trying to solve a problem in an innovative way. I really learned quite a bit in these years. And the team that we have grew as well. We started from just having one person looking at these models, and then we quickly realized that we really need bodies to cover all of these models. So we grew the team. Now we have about, I'd say 13, 14 people covering all sorts of models, from fraud, credit risk management, insurance, wealth, marketing, and there's, like Greg earlier mentioned, there's different algorithms in use as well, supervised, non-supervised, reinforcement learning. But basically, whatever's available out there, people are trying to use to solve, problems that the businesses have and bring in value to the bank. And yeah, that's me and my team in a nutshell.
Excellent. Thank you, Rustam. Thank you, everyone, for an excellent introduction about your background and the incredible work that your team has initiated around AI. So we see a lot of AI initiatives emerging around the globe across various industry and within banking field in particular. So my takeaway message is that to be at the forefront of innovation and to stay relevant as an institution, we need to adopt AI technology and of course adapt to its challenges. So the banks from other companies from different industries that have already adopted AI see clearly the benefits appearing, and there are numerous use cases within banks where AI is still being experimented with. And my understanding is from working with, I already reviewed some of the machine learning models, and from discussions with other groups, especially developers. And not only, there are groups within the bank that are calling for a more cautious approach towards AI adoption, because they want to protect the bank from any losses caused by using inaccurate AI models or by improper usage of correct AI models. So I guess I would like to invite everyone to pick a specific use case, discuss the challenges from the model implementation and model review, and feedback from model users, and how these challenges have been overcome. Feel free, maybe we can start with Maxime. He's been doing a lot of research, and he has more, he looked more at the pricing models and using various sophisticated deep neural network methods. So maybe you can choose your favorite exotic and just, maybe give, or it doesn't have to be a pricing. If you feel like, I'll leave it up to you to choose a specific use case, and just share with us some of the challenges from the implementation point of view and review from model users.
Sure. I mean, one of the nice things about doing machine learning in the context of pricing is that there's no black boxes. You're starting with a pricer that people know, understand, can run, and you're building a replica of that exact pricer. So it's not like you're feeding in some, credit information and trying to guess if someone should be approved for a loan or not. Like, it's literally, you're trying to learn a function and you're trying to see if you're matching it. So this gives you lots of tools to deploy when you want to both validate and move these kind of models into production. So at the baseline, you still have your original pricer, so you can A/B test them continuously during deployment. So one interesting thing you can do, for instance, is you have a pricer that's now 1,000,000 times faster than the old one, and you could route 1 out of every 100 trades to the old pricer to continuously check that you're in sync with the current market conditions. The other more aggressive type of testing that we've done is we're trying to research, like, how can you really put very solid guarantees on the performance of such models? And there's one technique we developed, which we call gradient ascent, which can only be applied actually in the context of pricers. So for any kind of classifier, you can't really do this. But when you have the oracle, which is the original pricer, and a replica of it, like the deep learning one, you can actually do the reverse thing that happens during training and actually climb the steepest hills to actively seek out the highest error points, meaning the places where the distortion is going to be the largest. And you might think if I'm in a very high dimensional space, it's very hard to find needles in the haystack, namely places where the error is high. But the cool trick is that even though the places where the error is very high may be very sparse, I don't know the expression in English, but the catchment basin, namely the roads that lead to this maximum, are quite big. And so you can actually verify using numerically in cases where you know the answers. You only need to drop a handful of pins and then climb towards the biggest error points to be able to get some good bounds on your errors there. So that's one example of where you can go about mitigating that risk.
Excellent. If there are any questions from the audience, we take questions along the way, or yeah, feel free to ask now, or yeah, in the Q&A session. I leave it up to you. Maybe from the validation point of view, a specific, yeah, you can choose your more recent ML model that was reviewed, and how did it fit within the regulatory framework and the validation framework? I know I'm going to ask Greg because I know you are RBC, you have two different model risk guidelines, which I was very impressed. And one is dedicated to AI ML models, and the other to the capital models and risk models. So maybe would you like to expand on that, elaborate more on the validation of, let's say, valuation model? How are the challenges from the validation point of view when it comes to ML models for applied to pricing or just risk calculations in general? Go ahead.
Sure. Yeah, I guess just kind of repeating what I said earlier. I don't think that the regulations are really the challenge. I mean, OSFI issued some basically a notification that they're going to revise E23 to handle some machine learning aspects, but I don't think there's too much, in my opinion, that needs to change there. I think the devil's in the details. So the example that I thought might be interesting for people is a NLP use case. They tend to be challenging to deploy in finance, I think, because the basically the corpus that you have available within the bank is typically pretty small relative to the scale of the training data that you need for such a model. So obviously people will take the pre-trained models that have been trained on whatever it is, Wikipedia or whatnot, and then try to apply them to finance. But the terminology used in the financial context is a bit different, right? Like the words have different connotations in the financial domain. So basically, the problem then is you have a small amount of training data to train the model to basically understand financial terminology properly. And the solution that we actually came up with to get around that is to use adversarial examples, which I thought was a pretty interesting approach. So a very, very popular technique in machine learning, of course, but effectively for people who are not familiar, effectively what we're doing is you're generating your own data set, right? By making subtle perturbations that are designed to fool the model to make it misclassify, and by generating those examples and then training the model on them, you can sometimes boost the performance. So so that was an example of kind of a challenge that you would encounter in the machine learning space that needs a special technique to overcome.
Great, thank you. Yeah, we will go over to, I mean, maybe the last question will be about regulatory AI and how do we defend these black box models to OSFI? But from how does it feed the ML model within the regulatory framework? So, and challenges around that. But we can elaborate later on this. Maybe Shelly, would you like to elaborate more on the OLI and some of the challenges? I know you gave an excellent presentation at BMO about from end-to-end product. But maybe would you like to share with our colleagues from other banks about the challenges that you faced and as far as implementation, and then feedback from the traders, and how was it used, that signal for
so thank you for that question. So Ollie, it didn't exist before, so I would have loved to have gone to the market and bought it, because it's much easier to buy it than have to build it. But it didn't exist. And so, the problem that we were solving for is that preventing operational loss was very backward looking. And so we weren't doing anything until something happened that was bad. So from a business perspective, the industry loses billions of dollars a year due to operational losses. And those usually happen because of input errors, missed execution, which means somebody just forgot to do something, or miscommunication. And those things usually happen within a group of people, whether that group of people is in trading or in operations or in payments, or it happens at the client. So at the beginning of the initiation of a transaction, whether it's payments or trading or retail even, the client could fat finger their own payment wire information or put the wrong account information in. Well, if we're assuming it's right, that wrong information is going to flow throughout the process. And so with Ollie, the problem we were solving for is, how do we get between the person and the misstep, whether it's input error, misexecution, miscommunication. And so that required data. And so we started looking at, well, what internal data do we have? Well, Basel regulations require us to capture errors and losses over $10,000. So we have that historically. We have people data, we have process data, we have a lot of historical data. And so how do we use that in order to identify when a group of people is likely to make a mistake? Well, you need more context. And so now we brought in external data, terabytes of market data and economic data. And then we said, okay, so let's train the model on a trading desk or in operations or payments to find the days where a loss is likely to happen, a human error, as we discussed. And so that is about training the models to identify high-risk days and then generating a signal. And that signal is a % likelihood of an event happening on a given day. Well, that's not even enough, because now we need to know when we need to take action or not. You can create a signal that is a 2% likelihood of an event or 99% likelihood of an event, but that's not good enough. We need to know the threshold below which we don't take action and above which we take action. And so the models get trained, and then we refine the signal by adding, additional internal data and having a lot of conversations with people that actually execute those processes. And so from a machine learning perspective, being able to create these proprietary models that will generate the signal that will help a specific group of people understand when they have a higher likelihood of an event, that's very valuable. But the challenges that you come across in doing something like this in a real life situation is finding the data, getting access to the data because it's there, but there's some type of protocol where you can't actually get access to it. Okay, so now you have to go over that protocol, then normalizing the data. And then if the data is big, if you've got terabytes of internal digitized voice data, for example, how do you move it? Right? Our big bank infrastructure isn't as nimble as we would like it to be. So you're constantly finding workarounds, as any entrepreneur, or in this case, entrepreneurs on this call often do, is you're finding out ways to navigate around the constraints of an organization like a bank to get data, normalize it, move it. And we ended up working off of our infrastructure. So Ollie is built in the cloud. It's cloud-based, web-based, and the architecture is scalable, extensible, and very nimble. Which has it's the reason we've been able to do this, is because we've moved off of our infrastructure and built Ollie in a cloud setting. So that's some of the challenges that we had, but Ollie is working today. It's predicting when we have likelihood of losses. We're able, we've got a process model now where we're pulling metadata out of processes, and we'll be able to identify when processes or steps in processes will break. And that will allow us to understand scenarios we can build to stress a process. And I think regulators are very, expect us to get ahead of these things, right? So doing the same thing we've always done isn't good enough anymore. So I think that the outcome has been hugely beneficial for us and the clients that we speak with who are interested in using it as well.
Excellent. Thank you. And if there are questions from the panelists too, regarding certain products or use cases that have been implemented at other banks, feel free to jump in and ask questions. I mean, the main idea of the conference was to see what our colleagues are working on, what are the problems they are trying to solve using AI, and just bring everyone together in one room and maybe not necessarily do effective challenge, but just share their knowledge and the steps towards implementing, adopting AI within banking. So I know Andrew Brown, he has an extensive, large group at CIBC and working at the enterprise level at various line of businesses using AI. Would you like to choose a specific use case? And
Sure. I mean, I could talk about NLP some more because, as I said, we do have a number of use cases around that, and it is, as Greg sort of touched on, it is very challenging because you don't have necessarily the large annotated corpora that you would want for doing that. And so so two issues, like one is just the vocabulary is different. Like the text we're looking at is very specific to our organization. It has a lot of names and brand names and things like that that don't exist in say Wikipedia, and so they're outside the bounds of your typical model. And so we've done some work around that, is trying to use transfer learning to augment a model and create essentially a CIBC word vector model, so that it can handle the unique vocabulary that's specific to our needs. And then sort of on the larger issue of just acquiring label data, you can only get so far with kind of unsupervised methods, because they tend to be not specific enough to be actionable. The results you get from say topic modeling or something like that, and so you really do want labeled data, but because of the sensitivity of some of that data, it's not like we can just go and crowdsource it the way that say universities or academic researchers would, right? They take a public data set and have some people categorize it or apply labels. And so that's not something, that's not an approach that's open to us. So we do have to use kind of internal resources to get their feedback on the data that we're using. And so one approach that's been successful for us is more of an active learning approach. So you can train a model on a limited data set, and then you want to acquire more labels from the domain experts in the business, but you want to do it as efficiently as possible because their time is valuable. And so looking for the examples that are sort of well classified, confidently classified by a model, and maybe sort of set those ones aside, and you apply the model to some unlabeled data, and look for the examples where it has the least confidence about sort of what the class or category is, and then send those over to the business team to apply categories, and then that sort of gets you the most lift from a limited training set. So that's like one example of a problem that we've been able to tackle using methods that are available in the literature, but may not be sort of applied in all use cases because you do have maybe a large corpora of data to train on. So yeah, there's a couple of examples of problems that we've tried to tackle in the organization.
Thank you. We will get back later to some other issues regarding AI. Armando, I want to hand it over to you. Your team has done an incredible amount of good work. Not long ago, I was one of the validators for a model that used by the market makers traders. So there are many other examples of incredible work done. Sent for review to validation from your group. So could you please elaborate or choose some specific use case that you?
Yeah, absolutely. I mean, I cannot, of course, get into the details of any of the of the models or use cases, but I can tell you some of the challenges that we had along the way, and definitely Shelly already mentioned some of them, and although would like to move fast and ultimately get to results in a most efficient manner, we cannot be as nimble as we can. So in fact, one of the main challenges actually is on the infrastructure side, getting access to infrastructure, which seems crazy to me given the size of an organization, but that comes in part being a regulated entity, and I think Andy also touched on that you cannot move data at the same speed as you could say if you were part of a tech company. There are additional considerations that have to be taken into account, especially when you're dealing with sensitive data. I mean, when you're dealing with capital markets, in particular on the trading side, there are certain type of models that are only using market data, so there is some flexibility there because you're dealing just with public data effectively. But it's still, I mean, the fact that you open a connection to one of the bank systems immediately makes you consider things slightly different, and you have to be more careful as you go. So one of the important things that we've done is understanding the rules of the game, and understanding meaning taking the time to read and understand regulations as well as internal restrictions. Very often you find that some of the hurdles are on someone else's interpretation of a regulation. So you do have to spend the time and again understand the rules of the game. And so with that comes, of course, the next step, which is identifying partners and owners of responsibilities within the organization. And that is important because you have to navigate many of the different departments. And in fact, in model validation, we have great partners where we rely on each other, and if we need to get something done, that is the most efficient way, because we don't have to go through so much red tape, but directly identify the most efficient way to get things done. And ultimately, what I say is, staying close to revenue generation has helped make some of our cases. There are business priorities that have to be taken into account, and that facilitates sometimes the speed to delivery, which goes in line with what I was saying earlier about some of the infrastructure and access challenges. But I mean, besides that, there are other contexts, and I think at some point you're going to talk about explainability. But one thing that I would say is that is a field that has evolved quite a bit in the last few years in active area research. And we have incorporated a lot of that to our models, effectively understanding why at a particular point a decision was made. Again, if it is a trading decision, there are risks associated with that decision. So it's important that we don't trust just the black box model, but we understand why that particular model chose to take action A versus action B as an example. and that has helped, of course, gain the confidence of the different partners and groups that we work with, which I think that is the other challenge, right? I mentioned revenue generation, but especially those the big impact type of projects, you need to have a team of people that will tell you the whole story. I mean, one of the things that happens with this type of groups on the technology or using technology is that, you know, they might not be experts on finance or whatever area of knowledge they're working with. So relying on those partners and gaining their trust is important. And how do we do that? Is, of course, by making them part of the process that ultimately is going to allow us to get those models to production, getting their information and their insights of how the different pieces work, and that ultimately allows us to go back and build the systems that are going to solve the real and more important problems. So one of the things that we've done is that we have embedded some of the people in our team as part of trading desks, and they, you know, stay there for as long as they need. Our group, or our AI group, is a centralized group from the front office perspective, where we encourage collaboration, where we encourage information sharing. But to get there, as I said, we send people to be part of training desk. They stay there for as long as they need, and they come back and start solving the problem together. A lot of what we do is related to time series type of analysis, and that is their area of expertise. And probably, as you all know, you would find a lot of interesting applications and a lot of interesting research, a lot of papers. But the things that truly work, I have not seen much publications on that, and I think that is because we're in the type of industry that once you figure something and it works, if everybody were to be doing the same thing, then it will not work it will no longer work. So it is an interesting challenge, right? You have information that you cannot share, but at the same time, there's a good spirit of collaboration, at least internally. That is what has kept us ahead of the game.
Excellent.
Yeah,
Yes,
that's it. Happy to take any questions.
Appreciate it. Thank you. And Ignacio, would you like to give us some updates about implementing ML models for counterparty credit risk? You guys are ahead of the game. We are all experimenting it with. So
exactly, yes. So basically, one of the big challenges, in fact, the big challenge that I've been working in over the last, not just now, the last, as I said before, 7 years. I started working on this on 2014, 2015, is how can we replicate a pricing function on a way that is very easy to compute, but that is very easy to calibrate. And that's the challenge. Because by construction, the pricing functions that we want to replicate are slow to compute. So we want a technique that is able to replicate, to create a replica of the function, but without having to call the function megazillions of times, but only a few times. And for that, something crucial is to understand that the place where these functions live is a risk management engine. It can be market risk, VAR, or FATP. It can be counterparty risk, and usually there is a huge amount of dependency in the data. For example, we know that even though the input to a pricing function could be the 5-year point of a yield rate of a yield curve and the 10-year point, these are two points, but you know they are very highly related. They hardly ever move independently. In fact, they move in parallel or maybe a bit of a tilt of the yield curve. So when we use that information, we can reduce massively the difficulty of the problem, because the problem that we have when trying to sample functions in general is the cross dimensionality, that as the input space, as the input domain grows, it becomes exponentially more difficult to sample that space. But if you're able to use the dependency in the data, then the effective dimensionality of the input space can be reduced to a few dimensions or a few tens, or in the worst case, a few hundred. Usually a few tens, it is in most cases. And then once you achieve that, first of all, you have reduced the problem massively, in the sense that you have the space that you need to explore. Therefore, the number of times that you need to call your pricing function gets reduced massively. Once you have achieved that, then you have, okay, once I have this dimensionality reduced space, do we use, what kind of approximative framework we use? And there are two clear candidates here that I discuss in great detail, as you can imagine, in the book that I just published. One of them is neural networks, and the other one is Chebyshev tensors. Each of them has, as always in life, has pros and cons, positives and negatives, like everything in life. And basically, the challenge here is to understand which one is better in which conditions. And that is one of the big challenges. And another one of the big challenges that has been referred to a number of times here is the famous black box effect, which is, and for that, Chebyshev tensors really outpace neural networks, in the sense that a neural network, at the end of the day, is difficult to understand what's going on there because of the complexity of it. That's the point of it. Whereas a Chebyshev tensor is basically, everything is analytically well understood. And also the error of the Chebyshev tensor has analytical expression as well. In that sense, these two alternatives compete with each other, and depending on the problem, of course, one or the other one is ideal. But the big challenge, so to summarize, the big challenge that we have in the sense of risk calculations, not only counterparty risk, but also market risk. In fact, this morning I had a long discussion about the models that we are going to implement for market risk here soon. And the challenge is how we can calibrate the replicating framework, however you want to call it, the machine learning framework, how we can calibrate it really efficiently and really in a way that guarantee that you need to call the pricing function very few times, that you need to have you have a lot of control. You understand what is going on in the box. You have a good control of the error. And also, very importantly, it always works. By this meaning that the last thing that you want is to have a framework that stops working in the middle of the crisis. That is the last thing that you want. You want something that you know that is going to work. Obviously, you can never say 100%, but with 99.9% of the times, regardless of the market conditions. And then reverting to what I said before, that is ideally achieved when you are calibrating your model constantly with new data. And you can only do that if your framework needs very few information in order to calibrate. So that is the kind of space that we are navigating, and is very interesting, as you can imagine.
Yes, calibration is, it's probably the most important when it comes to model design. Whether, the exposure number may not make sense if the calibration is poorly done. So,
well, let me say something. Sometimes it is wrongly said that a model is this, and you show the stochastic equations and the pricing equations. That is a wrong view of a model. A model is that plus the calibration algorithm plus the quality of the calibration data.
Right. Doesn't matter if it's one-factor model, two-factor model, three-factor model. If the calibration is not sounded, then the exposure numbers are probably meaningless. So,
and the same applies to machine learning methods. It's not just the framework; it is the data you calibrated it, the quality of the data. In my case, it's pricing function, so the quality is not a problem, because you can call the price a lot of times to sample the information. But then usually the pricing function is very slow to compute. That's because that's the reason why you want a machine learning method. Therefore, you want to call it as little as possible, and that's where the challenge comes, with all the controls, etc., that comes with it.
Right. But did you find it's more simplified? Like when we talk about machine learning model, we look mostly like non-linear fit optimization problems. So we kind of know numerically how to fit this models? Do you find there are some simplification going from PDE to just simple nonlinear regression? And
Yes.
Less
Well, exactly.
challenging.
Yes, I mean, of course, there are challenges when you move in that space. And let me emphasize it again, the direction in which we are going here in many ways. Of course, we also use neural networks, no doubt about it, because they are very useful. But also, I always say, a regression is to be used only when there is nothing else to use. Because the regression at the end of the day is a line that you pass through points, and you kind of minimize errors here and there, right? So if we can find analytical versions, numerical methods, which technically speaking are machine learning methods, that are able to replicate your function, that is the preferred choice in my opinion. And that is again, I'm saying this over and over again, Chebyshev tensors, if you are able to use them correctly, that's what they achieve.
Ignacio, sorry, I have a question. Neural networks and as well Chebyshev tensors are function approximators.
Yes.
What do you think is the advantage of the tensors when it comes down to calibration? Because maybe let's start there.
Yes, the advantage of a tensor, and also it has disadvantages, of course, let's talk about advantages, is that in a tensor, you have guaranteed exponential convergence of the approximator to the function that is being approximated under certain conditions that usually apply. And that is guaranteed analytically. It's not like usually it works, it is guaranteed. You can do the maths and it works. So that if you have the framework in which you want to implement it, and you, for example, are using, let's say the simplest case, one-dimensional case, you have 10 points and you have an accuracy of 10 to the minus 4. If you want 10 to the minus 6 from 10 points, 15, 20 points will achieve it because it is extremely fast. It is mind-blowingly fast. So that is the key component that a Chebyshev tensor gives you. And it gives you another one, which is you have absolute control of the error ex ante. Because at the end of the day, in a Chebyshev tensor, you are expanding your function in a series that you truncate, and that you know that converges. So the size of the last few coefficients tell you the size of the error that you are having without having to do anything else. So those are the two main strengths of Chebyshev tensors. What is the downside? Let's talk about the negative as well. The negative is that it is very sensitive to the dimensionality of the input space. So you need to first reduce the dimensionality, and then use the Chebyshev tensors in various forms. You have the brute, like the direct Chebyshev tensor. You have another type that is called in TT format that expands the dimensionality problem, deals with it. You have another type that is sliders Chebyshev tensors and slices of them. You have different versions of it to deal with the problem from that angle.
How can you handle products that are very sensitive to specific subregions of volatility surfaces with Chebyshev tensors? So I have in mind, a high dimensional autocallable with a basket of 3 to 5 assets. You're not going to be able to reduce that down to 10, 20, or 30 effective dimensions. It's going to be more like 100, 200, or 300 effective dimensions.
No, in fact, it's funny because this morning we showed the result that we obtained on that particular asset, that particular trade, autocallables of several assets. And in the concept of FRTB, we could, and this is strict numbers, we were passing we are passing all the FRTB P&L attribution tests that are very strict. And for each trade, we are calling the pricing function 36 times.
I mean, you probably have a very severe reduction in accuracy on that in that case, right? Because those are very sensitive to certain barriers.
We are passing the P&L attribution test for FRTB that, as you know, is extremely contingent, extremely, what's the word? Difficult to pass. And we are passing that perfectly. In fact, we are well inside of the zone in which we need to be. In fact, we are going to publish some paper on that soon.
Look forward to reading it.
Yeah.
Thank you. Much appreciated. Rustam, happy to hand it over to you. Challenges within from the model validation point of view, as far as reviewing ML models and defending them to OSFI. We are still experimenting, as I said. We haven't. Yeah. Go ahead. Go.
Yeah. So OSFI's E23 guidance is still applicable to machine learning AI models. Like it was earlier mentioned, they're trying to revise it and introduce some additional changes that explicitly mention AI machine learning models, and it's planned to be, rolled out and be applicable sometime in, I think, middle of June or middle of 2024. But even without those explicit mentions of AI machine learning related considerations, we still have E23 that covers the AI machine learning models, and we have, at least in my team, worked hard early on, 2020, I think, to revise our procedures in validating machine learning models and create kind of a process, a protocol, or testing procedures basically for machine learning and AI models. We did not create any separate policy for machine learning models. Our current enterprise model risk policy is still applicable to machine learning use cases and models as well. The main challenge was and still is working with third-party models. I believe what keeps me up at night is vendors refusing to provide information and collaborate. Vendor models is, it's another beast on its own to validate. There are also currently models from the cybersecurity space. Cybersecurity models are now in scope for model risk policy as well. We're trying to validate them. And that introduces additional challenges aside from most of them being vendor models. They also deal with a very sensitive subject, right? Cybersecurity. If you disclose the sauce, the secret sauce, your model is done, right? The bad guys, right? The perpetrators, if they find out how you do things, basically your cybersecurity framework is done. So it's extremely challenging to work on those projects. Aside from that, in general, for machine learning models that are more complex and more black boxy, I guess not black box, more like a gray box, the general challenge is explainability and fairness, bias. Or these were challenges in the beginning that we thought, and then after a few models that passed through our hands, a bit of literature review, industry search, reading papers, and looking at different implementations of different packages, different research papers out there, we quickly realized that this problem isn't really that big of a problem or unsolvable problem. There are solutions there to introduce post-hoc explainability, to assess model fairness, or even create fairness-aware models from the get-go. And it seems to be an ongoing research as well. There's a lot of different tools available, different methods of introducing explainability, and these are, most of them are model agnostic. Some of them are specific to certain algorithms. So there's a lot of available tools and methods out there. It's just looking at them and then reviewing their soundness and robustness, I suppose, and picking the best or the least troublesome of those methods. And on the model developer side as well, they seem to have realized that explainability and fairness are important topics, and they consider these when they build their models, which makes our job as a second line of defense easier as well.
Right.
And yeah, and I think the last challenge is not really from technical perspective, it's more from talent perspective as well. Finding good talent it's not easy, both for the first line and for the second line as well. For the second line of defense, it's double the difficulty to find a good talent because the nature of our job is to be able to criticize something and review something with an analytical lens. So you can't really do that if you don't really understand what you're trying to criticize and review. So that becomes very hard for the leadership to find good talent and retain talent as well, especially now that AI and machine learning is so democratized. It's very easy to get into the field if you have a certain level of knowledge already. There's tools available out there, off-the-shelf models. You can just import this and export that, and then build a model in 2 lines of code, and that makes you a data scientist. And you think you can build a model. So it's talent is one of the challenges, I think.
Right. Yes, I guess.
Letitia,
yes.
let me just correct one thing. Before I said 36 times, I just look at the numbers. I mix things up. It is 60 or 65 times, not 36. But anyway, it's very good anyway, just in case.
65? Okay.
65 times. Yes.
Okay, that's significantly. Yeah. Yes, thank you, Rustam. Yes, yes. As a validator, we always try to keep our independence as a second line of defense, and sometimes I guess what I came to realize is that the first question I have to developers when I see an ML model, I would say, have you self-validated the model? Like all this, used to be a time when a machine learning model were just a tool, like general AI platform. So as a second line of defense, you are not even going into alternative methods. So it's mostly the developers that carry all the burdens of implementation and development ML models. But the first question I have usually when I receive a ML model is, have you self-validated? And then we don't normally ask for more testing because it's already it is in the submission. The developers do extensive testing as far as explainability, fairness, and but yeah, it is. We are all learning along the way, and it is a challenge to defend again these models to OSFI as far as validation main challenge. So I guess Andrew, I know Risk Thinking has done an incredible amount of work as far as climate-based financial risk. This is a very, very hot area within the banks. At BMO, it's already developing, it's growing, it's a new group developing climate risk scenarios. And we still don't know how to do it. It's a new area, but I see it 5 years from now, it will be crucial within every financial institution. So would you like to, I know Thinking AI is at the forefront of innovation and leading, and everybody knows Dembo was the founder of Algorithmics, and Thinking AI is one of his babies as far as his passion for environment and climate risk, and now using AI it's definitely very challenging. So please let us share with us some of the challenges as far as climate financial risk.
Yeah, so challenge-wise, it comes down to having data that's interoperable and accessible. Like when you say, as Shelly was saying, there's terabytes of audio data that you have to sift through. There's terabytes of climate projections that you have to sift through, and that's just the physical risks. And then it's all the economic variables that you have to align to those physical risks. So really the hardest challenge that we had at the beginning was we had this great concept of how to quantify risk in a stochastic way. So Ron has this algorithm that he's patented that allows you to create self-generating scenarios as a spanning set following this particular mathematical concept that he's founded. So we thought, okay, great, we have the tool. This is how we're going to quantify risk. And then we realized that to actually make this algorithm work, we needed all of this data. And we needed a lot of data. We needed all the data for all time, for every scenario, from every model that's ever been run. So that was okay. We stepped back, and so to actually make this algorithm work, how do we get all this data in? And it took us about 18 months to just amass all of the data, clean it, consolidate it, now make it interoperable and interchangeable. And then to make that actually run as an application. So you're talking about there's a database that has the data. It's like, no, there's 5 different databases, and they all interconnect with microservices to transfer data from one side to the other and format it in a way that you can then use it in the models. So that was a really big challenge of just architecturally from the data handling side of how do you build the system that can actually hold this data and make it serve it up to models in a reasonable time frame. You can't take years to compute, or you can't take hours and hours or 3 days to compute something. You need it within 2 hours is fine if it's not live to a client, but you need it fairly within minutes if it's going live to a client. So there's a lot of those challenges of just getting the data in place so that you can actually run the models. And then we found that now that we have all this data, there's more that you can do with it. So you go down that pathway of look at all of this data, what else can we build? So you start building more tooling and more models on top of it. And that's where you can, if you don't have a really good end goal of what you're trying to achieve with this data, you end up building all this great technology that nobody ever wanted to begin with. So it's an old saying in tech and in startups, like, don't start with the technology, start with the customer and come back to the technology. And it's very true in this as well, because you can apply machine learning and AI concepts to anything, and they're all fascinating. And you can go down that rabbit hole, and you'll end up with something that's very cool to maybe the half of the people on this panel will think that's awesome. Nobody else in the world would even care about it. So you got to really focus what you're doing, and then start with that end product of what are you trying to achieve, and what tools and techniques get you there the quickest. And sometimes machine learning is the answer, and sometimes it's not. Sometimes just a simple correlation matrix will do, and you have to be able to see that. And that's where having diversity in people's backgrounds, and like one of the panelists was saying earlier, not just because you did a course online, doesn't mean you're a data scientist. You can pull this information, or pull from a diverse group of people that have an interest in data science or an interest in machine learning, that come from different backgrounds, and they have different views of how to apply these things. Like on my team, we have ecologists, like PhD ecologists, we have pure mathematicians. One of our ML engineers, one of the main engineers, he's a medical doctor. He did his MD, he's a doctor. Decided that in his research for his MD, he was using like wavelet analysis to decompose EKGs and doing predictive analytics on heart attack potential in patients. So he's taken that knowledge and that background and that diversity, and he's applying it to now financial economics, same as I'm sure Armando has done with his physics background, applying it to a diverse field. So it's really about finding those diverse people, those diverse viewpoints to say, here's this problem. Now, how do we solve it? Go back to that first principles, find the tooling that works, not just because it's cool, but because it's actually applicable and gives you the best results. And sometimes they'll end up being this really cool thing. You have knowledge graphs and ontologies, and you're doing NLP and building, used the Roberta model and applied it to climate science. So we have a ClimaBERT, we call it. But you end up with something cool, but sometimes it's just a regression analysis and a correlation matrix and basic statistics gets you 90% of the way.
Thank you, Andrew. Yes, it's a challenging, and I think right now we feel like AI can solve all the problems, and eventually, come to what's the future of AI. We may think that AI maybe will overpower humans in the future, and I hope that's not the case. We still need our human brain to do analysis and interpret and give meaning to the outcome. Just a number. You have thousands of regressions on a network. Doesn't mean that any number that comes out, it's also the right number. So we still have our human brains and mathematics and physics knowledge required to give meaning to these numbers. So I will skip the next question about data because every speaker touched upon data, and we within banking we know that whether it's internal data or external data, we have lots of challenges even sourcing the data and applying it in large volumes to various for different purposes of the models. And so I will skip that, and I will go to the building trust in AI. So as artificial intelligence gains popularity in the banking, it is attractive from the it is attracting attention from the regulators, and that's the question that I am after. In the end, the application of AI in banking has many benefits, such as higher efficiency from automating banks' internal processes, accelerating innovation. We like to talk about AI at the forefront of innovation, and enhancing customer experience, like instant credit application decisions. There will be actually a discussion from 4 to 5. One of the papers will talk about this application, credit application decisions using AI. And however, it also has some drawbacks, including the potential for lack of transparency and bias in the algorithms decision, and potential risks to financial stability. So explainability is one way to ensure fairness. So it refers to understanding how and why the algorithm makes predictions. For example, explain why a fraud detection model flagged a particular transaction as fraudulent. So I would like to, each of you, or it's up, I leave it individually to decide whether there is much to elaborate other than, yes, we've seen some papers on model explainability, and now it's becoming, it's rapidly changing. There wasn't much to read like even 8 months ago, and now it's like everyone is publishing from different angles around model explainability, and this is something that we like to sell the ML models to us. We're using a detailed and more understanding on the predictions using this will be an additional tool on top of ML is model explainability, retraining, or depending how it's designed by this tool. Would that be enough to give us to trust the AI model? So I leave it up to you, to everyone in the audience to jump in and to share some of your views on this. How much is needed to trust the AI, and why model explainability maybe is probably the bulk of understanding, and other regulatory. Yes.
I would just jump in. I think we only have 3 minutes left, so I'll give a 30-second summary here. I think that, I gave this example of if our businesses are going to drive fast and take chances, we have to have the ability to, have the right airbags and seat belts, ability to see around the bend and stop on a dime. And so as our businesses become more sophisticated, our ability to manage risk has to become more sophisticated. And that includes managing risk around AI, machine learning, and the models that we create to enable our businesses to take chances and drive profitability. And that we have already frameworks in place where we have 3 lines of defense. We have policies, procedures, guidelines. We have processes, controls around, sharing data, privacy, and other controls there. And so I think that we need to work within the frameworks and then enhance them as we continue to introduce more sophisticated risk-taking and risk management into our businesses.
Excellent. Thank you, Shelly. Greg, would you like to add more on this?
Sure. I guess I would say that to some extent, at least, explainability is something of a red herring. I think there's soundness perhaps broadly covers what one might call robustness. I think robustness is far more important. So basically, robustness meaning that you have good reason to believe that the model's not going to break, and there's many things you can do for that. You can basically model monitoring in short, right? Like if you have good model monitoring, if you know when the model's performing well, when it's not performing well, and you can act accordingly. To me, that is much more valuable than explainability for trust. Explainability carries with it a host of challenges. I mean, the first one is what you mentioned at the outset. If you're building a model to explain another model, well, now you've got two models. So now you have two models to validate, not one. So I tend to think of explainability as being kind of used from a model validation perspective, used as a spot check. But you shouldn't rely on it 100% to trust your model. You really need to check that the robustness is there. Where I think that explainability is very useful is when there's somebody actually asking for an explanation. If you have a client coming to you and saying, "Can you explain to me why this credit decision was made the way it was?" Then explainability is very useful. And like I said, then you need to validate that the explanation actually works, because that explanation is going to be very, very important to the client. It seems that OSFI in their latest guidance, they've changed their stance somewhat, where in their previous consultation they tied explainability to materiality, but in their most recent memo they've tied explainability to use. So I think that gets to what I'm saying about explainability being mainly needed if somebody's asking for an explanation. So that's my stance on that one.
Great, thank you. Maybe Andrew Brown?
Just quickly, I think a lot of things have already been said and covered about the explainability issue. Certainly, like one of the things I find when people are asking for machine learning or AI to be applied to a problem, they're actually looking for that explanation as much as they are looking for a predictive model. And one of the trends I've noticed, at least like some parts of the academic literature, they're revisiting some models that are inherently interpretable. So going back to decision rules and decision trees and saying, well, these things that were designed, algorithms that were built in the 80s that were sort of heuristic because we couldn't computationally, they were intractable. Now we have a lot more compute power, we have new algorithms. Maybe we can actually go back and revisit these methods that are inherently interpretable. A human being can look at them and understand them. And we can still not sacrifice much performance as well. So I think that's kind of a trend that's worth exploring. We've done a bit of work at CIBC along those lines as well.
Appreciate it. Yes, that's a good time to stop. Maybe I will take one more view on Maxime's view on model explainability and trust around AI model.
Sure. I mean, I think when I hear the words robustness as being more important than explainability, I think that resonates strongly with me and the approach that we take to our models. So for instance, for me, you have a neural network that's replicating a pricer. How are you going to get comfortable with this performance? Well, first, you're going to do the usual things, which is test it out of sample and all that jazz. But then in terms of robustness, you can kind of go and find those points where you're finding the highest errors. And then since you do have an oracle, i.e. the original pricer, you can then do sweeps along most problematic dimensions and see how the model behaves in those difficult spots. And the behavior that you end up seeing, which makes you comfortable with the models, is that they're very, very stable in those regions. So there's this common misconception about neural networks that when you're outside of bounds, they tend to wobble. And people think that because they're used to the polynomial effect, right? So if you're fitting a polynomial to a handful of points, you'll get these Gibbs phenomenon where it's flying all over the place. And the cool thing about neural networks, especially deep neural networks, is that they have a low frequency bias. So they learn signals from low to high frequency. So whenever you're kind of going in those problematic regions, even getting closer to the edges of domains, you'll get that nice smooth behavior. And this ties right back into showing that they're robust to perturbations.
Excellent. Yes, that's the main takeaway. That it's a model robustness. Whether it captures all the features that was or designed by design meant to be used by the ML model and have more confidence in the outcome. I'll stop here. Sorry, I was trying. We are running a little bit out of time, and I would ask the audience if they have questions, please, please address them to a specific speaker. And feel free to reach out to each of the speaker and just take it offline if not necessarily we don't have questions now, but later on. Yeah. These are the right people to reach out and ask about machine learning in banking. They are our subject matter experts, and I'm really pleased to have everyone in the same room. And I know AI, there is a lot of pushback from banks, and banking is catching up with AI and ML models. But there is a lot of good work that has been done, and I'm happy that everyone had the chance to share this knowledge with our colleagues from other companies and startups and banks. And
thank you, Letitia.
Thank you.